The first talk of this morning is given by Timothy Budd from Nijmegen. Am I right?
You're right.
And we'll talk about lattice walks on the left and planar maps on the right, or maybe the other way around?
Let's see. Okay, thanks Nicolas. Thanks also to the organizers, who not all are here, but still thanks. I have to turn something on, I guess. But luckily this quote is not recorded on video. Yes, can you hear me now? Better. Okay, so in the past week we've seen various ways to count planar maps, study random planar maps. For instance, we've seen in Gregory's talk, who gave a marvelous introduction to what I'll be talking about, that one can study these walks through, say, labeled trees, going back to Schaefer's bijection in the 90s, but also the Bucce di Francesco guitar bijection. There is a peeling kind of method that I'll describe that dates back to the 90s, and also is quite useful to study kind of random aspects of planar maps. And then in more recent years, we've seen a lot of kind of mating of trees type bijections, which relate planar maps to lattice walks in 2 dimensions. And each of these types of bijections have their own merits, and sometimes it's not quite clear how these should be related to each other. So what I'm going to talk about is kind of a first step in trying to relate lattice walks in 2 dimensions to the peeling process of planar maps. Okay? So here is the plan of the talk, and again, I'm quite grateful to Gregory, who gave a very nice introduction on Boltzmann planar maps and the peeling process, which I'll briefly review. And then I'll start discussing how one can relate random walks, so I guess this is the pointer, random walks on the 2-dimensional lattice to Boltzmann planar maps. And after that, I'll see how far this can be extended to a statistical model on these planar maps, which is the ON loop model. And in particular, I'll discuss the peeling exploration of such a loop model decorated map. And I'll look at some connections between the nesting of loops in these maps and something called the winding of these random walks. And finally, at the end, I'll discuss to what extent we should expect that this connection leads to a version of the mating of trees that could apply to, say, the O2 model. This will only be in the very last part of the talk. Okay, so a reminder about the Boltzmann planar maps that Gregory introduced. So he denoted the set of rooted bipartite planar maps of perimeter 2p by m sub p. So here's an example of such a Boltzmann planar map. It has perimeter 12, corresponding to the number of edges sitting on the outer face. It is rooted and it's bipartite, so all faces have even degree. And he took a sequence of weights, Q1, Q2, etc., which are all non-negative, and defined the measure W of some planar map M to be a product over all faces of the weights associated to the faces, with the index being equal to half the degree of the face. And a weight sequence called admissible if the kind of total weight on all possible planar maps of fixed perimeter is finite. And in that case, one can normalize this measure to a probability measure on this set. And that's what we call the Q Boltzmann planar map of perimeter 2p. So when we have a planar map, in particular a bipartite planar map, we can look at a particular exploration process of this map called peeling, which dates back certainly to the 90s to Watabiki's work, but perhaps is kind of a natural extension already of Tutt's work in the 60s. So one way to formulate this peeling is to say that we consider a nested sequence of submaps of the planar map that I'm exploring, whereas submap is really a planar map with certain faces and special faces, which are the gray ones here, which are kind of the unexplored regions in the map. So one should think of this nesting as a sequence of kind of our current knowledge of the planar map as we discover it. So in particular, when we start just by knowing the perimeter of the map, then we have a hole inside which we do not know what sits there. And then we can discover kind of faces in this map one by one. But it can also happen that we discover or try to discover what sits on the other side of one of these faces, and we find that the edge is actually adjacent to an edge on the other side of the hole. So let's be precise. So we want to take a planar map, a bipartite planar map, and turn this into a deterministic process. And to do this, we fix a peeling algorithm, which, given such a planar map with the distinguished kind of unexplored faces, it returns to us an edge that is incident to one of these unexplored faces, one of these holes. And then we say that the peeling process, given such a planar map with a hole and an edge incident to the hole, it reveals what sits on the other side of this edge. And as I said, it can be a new face. So in this case, I'm revealing what sits on the other side of the root edge, which is this one, and it's a new quadrangle of the map, and I insert that into the hole. Or it can happen that what I try to reveal on the other side of this edge that I've selected is actually so this edge here, it's the outer face again, so I have to glue this edge to another edge of the hole. Okay. And Gregory described that if you do this for a Boltzmann planar map, that what you get here is really a Markov process which has very simple transition probabilities which follow basically just from Tutt's equation of Boltzmann planar maps. So to determine whether I find a face on the other side of such an edge or that is glued to kind of another edge on the boundary of the hole, one has really just to determine what is the total weight of all planar maps that can sit inside of these holes.
You had marked faces sometimes. You don't have that?
So that was the version without the marking. So there is another version, which is the targeted peeling exploration, thank you, where we consider now a planar map which has a marked vertex. And we can go through the same procedure, but now as we explore the map, we keep track of the hole that will eventually contain the vertex. And again, one can work out the transition probabilities for such a peeling exploration, and this Gregory also did. And it's slightly different because the total weight of all planar maps that have a marked vertex is slightly different from the weight of maps that do not have a marked vertex. Okay, let me go there soon. So if in a Boltzmann planar map one keeps track of this face that contains a marked vertex, and one takes the perimeter of this face, so this is the perimeter process, Pn. So here it starts at a perimeter which is equal to 4, so that's the half length of the boundary of the unexplored face. It can increase if I find some new face, or it decreases when one of the edges is glued to another edge. Right? So here I've selected a peeling algorithm that every time selects an edge on the face that contains the marked vertex in the end. And then what I get is a process, Pn, that in fact is a Markov process because of the Markov properties of the Boltzmann planar map. Now, some of this is a bit theoretical, so sometimes it's nice just see how this looks like and actually to look at some peeling exploration of planar maps yourself. And luckily you can do this. So there is this applet on my website, which you can find if you follow the URL in the slides. So let's try to peel a Boltzmann quadrangulation of perimeter 8 here. So what I've done, I've just created here a face of degree 8, and I've pressed so I selected a face and I pressed U to make it an unexplored face, to make it a hole. And then what we can do is we can say, suppose we explore a face of degree 4. What can happen also is that I find, say, let's see, that two of these edges are glued to each other, and the applet has the kind of the various operations built into it. You can also just press P, and it will act as if the holes in this planar map are actually kind of critical quadrangulations. So quadrangulations are special cases of the Boltzmann planar map where all weights are taken 0 except for Q2, because that's the weight I associated to quadrangles. And one can just see how this exploration process goes. So here is an example. Let's see if we can explore the full quadrangulation. Okay, for now I have produced for you a Boltzmann quadrangulation of perimeter 8.
What's the algorithm to embed this that you're using here?
So this is a force-driven embedding. Yeah. So it's certainly not one of these conformal type embeddings, but a pleasing one. What we can also do is tell the app that this is a marked face which should contain a marked vertex. So now we're going to explore a quadrangulation with a marked vertex. Let's see whether we can actually discover the marked vertex. So we already saw at some point that the face was split into two unexplored faces. One of them contains the marked vertex. Now again we have this splitting occurring. So now we see here we have two unexplored faces, one of them containing the marked vertex. Now one can continue. Let's see whether it will actually find the marked vertex. This is when probability is not your friend, but we have a good chance. It's pretty small. That's well, there we go. So we just generated a critical Boltzmann quadrangulation with a marked vertex. Very well. So are there questions about this peeling? If not, yes.
So, Mark, when you have your two faces, you continue exploring both, depending on weighted by the actual probability that the marker is there. You don't choose. Because sort of you started exploring both.
Okay, right. So what I discover really does not depend on how I choose my peeling algorithm. So in this case, I just randomly selected one edge and one of the holes to explore.
So you don't choose the hole as when you see that it splits, you just do you continue exploring both.
You can do whatever you like.
But that's in the app.
Yeah. Here. Okay, so here's the link if you want to try it for yourself, if you don't like the rest of the talk. Okay, so let me return to the reminder of Gregory's lecture. So we're looking at this perimeter process of the size of the hole containing the marked vertex. And he described that one can actually study this Markov process quite easily by kind of realizing that it has the law of a random walk, Sn, on the integers, with a particular law that depends explicitly on my weights Q. So to go from this random walk to the perimeter process, the only thing one has to do is to take the random walk and condition it to hit the negative half axis at 0. And this can be done by an H transform, where the H function that you're using is completely universal and does not depend on Q. So the explicit transition probabilities of the perimeter process are given by this function. Okay? And Gregory also mentioned kind of a result that all possible laws on random walks one can get here, for all possible admissible weight sequences Q one can choose, correspond exactly to those random walks for which the probability that it hits the negative axis at 0 is given by this function. So let me reformulate this result slightly and then state it precisely. And for this it's useful to look at the Wiener-Hopf factorization of the random walk S. So let's denote for the random walk S the strict descending ladder process to be the levels of the consecutive minima of this random walk. And the weak ascending ladder process is the levels of this random walk at its successive weak maxima. And then it's a classical result in random walks that if you know the law of the ascending and the descending ladder process, then you also know the law of the random walk itself. And more precisely, the characteristic function of the random walk factorizes into the characteristic functions of the descending and ascending ladder processes. Okay, so why is this useful? Well, if you know the descending ladder process, then of course you know where it will hit some negative half-line. So requiring that my random walk hits a negative half-line at some value with a particular probability is asking the same for the descending ladder process. And it turns out that this requirement that the descending ladder process, when started at p, hits 0 or hits the negative half integers at 0 with this particular probability, it completely fixes the law of this descending ladder process. So what we have is a bijection between admissible weight sequences Q and laws for random walks on the integers, such that the descending ladder process of the random walk associated to this law is some universal process. And moreover, the weight sequence is critical exactly when the random walk oscillates, and in terms of the ladder processes, this is equivalent to asking that the ascending ladder process is not defective. So what do I mean? So if this random walk Sn would say drift to minus infinity, then at some point I would never encounter any weak maxima again. So this random walk would have a probability law that sums up to something smaller than 1. If this happens, then the corresponding weight sequence Q is subcritical. Well, if it's non-defective, then Q is critical. Okay, so let's identify what this law of the descending ladder process is, and I call that T of I. So it's a unique strict descending random walk that hits the negative half integers at 0 with a particular probability, which is this central binomial coefficient. And it's easy to identify some process that does this, because this is just a probability that a random walker returns to its starting point after 2p steps. Or formulated differently, I can take a lattice walk with just northwest and southwest steps, starting at p, and then asking where it will hit the negative half axis. Now of course it will hit this negative half axis at 0 exactly when the random walk is 0 after 2p steps, which is this probability. So the descending ladder process is exactly equal in law to the axis intersections of such a random walk on the two-dimensional lattice. Right, so if I started at p, so t0 is equal to p, then t1 will be the next time that it returns to the axis, etc. Now, there is a very particular value of q, namely q equals 0, so putting all weights equal to 0. That corresponds to Boltzmann planar maps with no interior faces, so these are just Boltzmann trees. Or not really Boltzmann trees, because I'm fixing the perimeter, so I'm looking at uniform trees of number of edges, which is half the perimeter of the map. Now if there are no faces in this map, then the peeling process will never increase, because it can only increase or stay level if I discover a new face. So my perimeter process will always decrease, meaning that the random walk governing the perimeter process is strictly decreasing, and hence it's equal to its descending ladder process. So in fact, the peeling process of a random tree really corresponds to the axis intersections of this random walker. And it's not so hard to imagine that actually one can really find a bijection between such walks on the lattice in these trees, because every excursion here, if I squash it in the usual way into a tree, it will actually describe what I see in the map. So my plan is to take this a step further and look at more general random walks in the two-dimensional plane and see whether I can associate to that not just the peeling process of a Boltzmann planar map, but a full Boltzmann planar map. And here's an indication that this might be possible. So let's consider a two-dimensional random walk, x, y, such that x has independent increments in the integers plus 1/2. So what I'm looking at are really random walks that do not walk on the integer lattice, but on the half integer lattice. But I want it to be in such a way that when it returns to the axis, that it does this at kind of integer values. So then I have to choose the vertical walk y of t to be a independent simple random walk on the half integers, and the horizontal walk x to take steps that are an integer plus 1/2. Okay. So these are walks with such kind of steps. And here is a result. So the law of the sequence of axis intersections of this two-dimensional process is equal in law to some random walk associated to the perimeter process of a Boltzmann planar map, precisely when this horizontal random walk does not take like steps to the left which are larger than 1/2, but it can take arbitrarily large steps to the right. And also one has to require that this random walk does not drift to the right, because otherwise I would not get an admissible weight sequence Q. And I'll describe to you in two ways how to understand this result. The first is a magical 3-line proof, which relies on a work by Mireille Bousquet-Melou and Gilles Schaefer back in 2002, where they counted walks on the two-dimensional plane with a slit in it. And the basic idea is that if we want to look at the axis intersections, because those are supposed to correspond to this random walk, then we have to take the horizontal process x and take its values every time that y is equal to 0. So that corresponds to subordinating x by this process t of I. And the magic is that subordinating a process x by this t of I commutes with the Wiener-Hopf factorization of x. So what do I mean by that? Well, subordinating kind of the characteristic function of x by t actually corresponds just to taking a square root, while factorizing the process into its descending and ascending ladder process corresponds to factorizing its characteristic function up to the kind of the 1 minus. But okay, taking square roots and factorizing, that is a nicely commutative operation. So what one gets is that the Wiener-Hopf factorization of the subordinated process is really just the subordination of the factorized process. And I already know that the such a random walk S is going to correspond to an admissible weight sequence if it has the right descending ladder process. But by this result, having the right descending ladder process is equivalent to saying that my process X has to have the right descending ladder process. And what do I mean by the right? Well, the same descending ladder process as the X component of this walk, which is just a linear function. So the descending ladder process is also just a linear function. So I need my process X here to have a descending ladder process that is the linear decreasing function, which you exactly get when the walks only have like the minimal step to the left. So somehow the magic here is in this commutation of subordination and Wiener hop factorization. Let's see a more combinatorial kind of argument why this works. And the combinatorial idea is to look at fragmentations, both of planar maps and of lattice walks. So the peeling process of a planar map, and okay, I have to apologize a bit here because now I'm switching from bipartite planar maps to more general non-bipartite planar maps. But okay, the peeling process works in a very similar way there. So I can look at a peeling process of a particular planar map like this one, which, as Gregory explained, is like applying touch decomposition in an iterative fashion. So removing the root edge and then see what kind of fragments remain. And doing this until you're left only with vertices. So what you get in the end is a kind of a bipartite, a binary tree where each kind of branch in the tree corresponds to one of these decompositions of the map. So this is really a dual description of the peeling process to the one that I described before, where I view the planar map as unexplored and I kind of decrease the size of the unexplored holes in the map. Here I'm starting with kind of what I know about what sits inside of the holes, and I decompose this interior. But it's really the same thing. So for instance here I remove the root edge of the map, and then I see that, okay, I find a face of the map which is a triangle, and then kind of remaining part of the map. So if I fix a peeling algorithm, then deterministically, given a planar map, I get one of these binary trees, where each of the leaves of the tree corresponds either to a vertex or to a face of the map. And it's convenient to label this tree by associating to all of the leaves a certain number, which is the degree of the face of the vertex minus 2. So here I have a bigone, so I associate a 0. And if I have a vertex, I associate a minus 2 to it. And then I just add up these labels going down the binary tree. And it's not so hard to convince yourself that the labels on these inner vertices, which are really planar maps, correspond to minus the perimeter minus 2 of that map. Right? So here I have a map of perimeter 4, so I get minus 6. So up to a minus sign, one should really think of this as like a fragmentation process. So I have a fragment of size 8, which fragments into sizes 5 and 3, etc. So let's look at a similar fragmentation of lattice walks. So now I'm going to start with a lattice walk in the upper half plane of the integer lattice. And I've slightly generalized the type of steps that my random walk is allowed to take. So we can take integer steps in both coordinates, but I require that the vertical coordinate can change by at most 1, and the horizontal coordinate can change by as much as it like to the right, but it can only take like 1 step or distance 1 to the left. So here's an example of an excursion of such a walk in, say, away from the x-axis going up. So I require the walk to return to the axis only at its endpoint. So what is a natural way to fragment such an excursion? Well, I look at the first time that my random walk returns to level 1. So then this first excursion away from level 1 gives me, again, an excursion from the axis. And then I can take the remainder of this walk by here and then adding on to it the first step, and that will give me another excursion away from the axis. So again, I can keep on fragmenting this, and the fragments will get smaller and smaller until at some point they will only visit level 1 just once, after which it cannot kind of further fragment it. So actually what the fragmentation I'm showing here is not quite complete, because I can fragment this one a bit further. We're taking the excursion between here and there to be just a single step to the left. But that won't matter in the following, because I'm going to take a subset of this excursion to relate to the planar maps. Okay, so a natural way to label these excursions is by looking at kind of the place where it returns to the axis, which I call the extent of the excursion. So this is an excursion of extent minus 8. And whenever you fragment, then the extents of the smaller excursions will add up to the extent of the larger one. Right? Now, given such a binary tree with these excursions on them, one can always find a maximal subtree for which all inner labels are smaller or equal to minus 3. And such that all the nodes of the tree have labels larger or equal to minus 2. So why exactly is this true when I take the boundary to be at minus 3? Well, whenever I have a fragmentation of size minus 3, then I know that it has to visit level 1 at least twice. And this is not necessarily true if I take a fragment of extent minus 2, because here, for instance, it visits level 1 only once. So here really comes into play that my walks are not allowed to step far to the left. Okay, so I got this binary tree with labels on them, and if you paid attention, you actually see that I get the same binary trees on both sides with the same labels. So in fact, what one can do, when you can extend this procedure as a bijection from the excursions in the upper half plane of extent minus p minus 2 to planar maps with boundary length p, just by matching these trees. But then, okay, on this side, if I know all the labels on the leaves and I know the structure of the tree, then that completely determines my map. Well, on this side, I still have kind of these walks sitting on the leaves. And they correspond exactly to the vertices and faces of my map. So to make this into a bijection, I really have some decoration on the faces and vertices of the map. So explicitly, what is this decoration? Well, for each vertex, I have an excursion. So a vertex corresponds to a label minus 2, so it corresponds to an excursion that starts at 0 and ends at minus 2. Now for every face, I have a label, the degree minus 2, so it corresponds to an excursion that starts at 0 and ends at the degree minus 2. Now I've slightly cheated when I did this, because I kind of assumed that in these binary trees there is always a canonical ordering of the branches. But this is not quite true for this fragmentation of the planar map. Certainly when I remove the root edge and I get two disconnected components, then there is a component sitting at the tail of the root edge and one sitting at the head, so that gives a natural ordering. But if I remove a root edge that does not disconnect the map, and instead you find a face in another planar map, then there is no kind of natural way to order these two. Well, certainly on the fragmentation of the excursions, there is a natural ordering. There's just the first excursion you encounter and the second one. So to really make this a bijection, what you have to do is take these excursions that sit on the faces and kind of keep the information whether it's sat on the left or the right. And a convenient way to do this is to either take the excursion above the axis or below the axis, determined by whether what's on the left or on the right. So in fact, the labeling I get on the faces corresponds to excursions either above or below the axis of extent k minus 2 for each face of degree k. Okay. So this is a bijection. And it naturally extends to planar maps, or kind of different versions of planar maps, for instance one with a marked vertex, where now I do not look at excursions above the axis, but walks that start on the axis. They can walk anywhere in the plane while avoiding the negative half axis and end at 0. In that circumstance, the natural way to decompose such a walk is to look at the first point that it returns to the axis. So that gives one excursion above the axis and another walk on the slip plane. Another way to think about this is kind of starting from my fragmentation of the unpointed case. If I mark a vertex, then I remove the decoration that's set on this vertex, and I replace the corresponding leaf in the tree just by kind of the trivial walk on the slit plane that starts and ends at 0. And then I can really regroup all these excursions back into a walk on the slit plane. Similarly, one can look at Boltzmann planar maps that have a marked face without decoration. So a perimeter P and a marked face of degree L. And these are really in bijection with walks on the slit plane that start at P and end at minus L, hitting the negative half axis from the top. Okay, so we have these three types of bijections. So how does this explain the result about the perimeter process I described before? Well, of course, we can just take these walks on the left-hand side to be random walks. They will produce for us certain planar maps of decoration, and I can just forget the decoration. And it's not so hard to kind of convince yourself that kind of the weights associated to the faces, the kind of the probability distribution in this planar map, is really of the form of a Boltzmann planar map, with these weights corresponding roughly to the kind of the return probability of an excursion to the axis. So in fact, we get a Boltzmann planar map with a weight sequence Q that is given by kind of its measure on the integers corresponding to the return distribution of the walk to the axis. Now also what one can notice, if we have a marked vertex here, and we look at the axis intersections of this walk ending on the slit, that it really corresponds to the perimeter process of my peeling of this map. If my random walker, the x component, has no drift, then my Q will be critical. And the scaling limit result is that if my walker has an x component that is in the domain of attraction of an alpha stable process, which is necessarily spectrally positive because it cannot have large jumps to the left, with alpha between 1 and 2, then the perimeter process, or its random walk, is in the domain of attraction of alpha over 2 stable process. Now if you recall from Gregory's talk, this was true quite generally for Boltzmann planar maps. However, the exponents that I get, they correspond to what he called A between 3½ and 2. While the full range of universality classes of Boltzmann planar maps is between 3½ and 5½, with 5½ being the Brownian map universality class. So using these lattice walks, one can get Boltzmann planar maps in the universality class in this range, which are quite different from the Brownian map. And in fact, they correspond to the ON model gaskets in the dense phase, which I'll get to soon. Okay. So as I said, there is some connection with the ON loop model here. So let's see already a glimpse of the loops before I make this precise. So suppose I take a random walk which is symmetric, left-right symmetric. Then I said that if you take this random walk and you stop it when it hits the negative half axis, so that's a a walk on the slit plane ending on the axis. So it encodes a planar map with a marked face, with the degree of the marked face corresponding to the endpoint of this walk. So let me just insert some padding there, a loop, and look at the next part of the walk until it first reaches the positive half axis. Now by symmetry, this is again like a walk on the slit plane ending on the half axis. So it also encodes a planar map with a marked face, which I can nicely put inside of the hole that I have remaining in this map. And finally, here I have a walk that ends at the origin while avoiding the negative half axis, and this encoded a planar map with a marked point, which again sits nicely in there. So in fact I get a bijection between, say, simple random walks or any random walks with a symmetric distribution, and planar maps with a perimeter 2p corresponding to the starting point of the walk, and a number of loops that are kind of nested around the marked vertex in the map. And again, there is some decoration on all the faces and vertices of the map. But if I forget about this decoration and take my walk to be random, then what I get is a Boltzmann planar maps together with kind of these nested loops sitting in there. And in fact, all the loops carry signs because the walk can end at the top or the bottom of the axis and both encode the same map. So I have to record whether it hits from the top or the bottom, and I do that by putting signs on these loops.
How do you get G? Where does G come?
Okay, so to be precise, so I not only have these excursions sitting on the faces, but I also have excursions sitting on the vertices. So this corresponds to Boltzmann planar maps. We have not just weights on the faces, but also weights on the vertices. And as Gregory explained, if you have this, you can reabsorb them into the weights on the faces using Euler's formula. But if there are kind of boundaries in the system, then these will also get contributions. So this G that you get here is exactly kind of the contribution of the weights that sit on the vertices that you've kind of moved from the vertices to the boundaries of the map. In this case, they end up on the loops and also kind of on the boundary, but the boundary length is fixed, so that one you do not notice. So there is some explicit formula for G here. And what is more, so if you look at this random walk, the natural question to ask is how often does it wind around the origin before hitting it? And it's not so hard to see that this is exactly just adding up all the signs of the loops on the right hand side. Because every time it went from the positive half axis to the negative half axis, the winding angle changed by plus pi or minus pi, where the plus or minus really corresponding to the signs on these loops. Okay, I think I have about 2 minutes, or 5, very good. So this smells like a loop model on planar maps. Let me briefly recap this. So I look at all planar maps, bipartite planar maps with fixed perimeter 2p, with some loops drawn on the dual graph. And there is a nice way to sample kind of a uniform or a random element among these, which is called the rigid ON loop model, where each of such random maps receives a weight, which is now just a Boltzmann planar map weight, but also some weights on these loops. So I get a factor of n for each of the loops, a factor of g for each of the faces that is intersected by a loop. And if this weights sum up to something which is finite, then I can normalize it, and this defines for me the ON loop model on the Boltzmann planar map. Now, Gregory also mentioned that if you take these weights to be sufficiently small, so this being admissible, then the gasket of my planar map, so what is the gasket? So the gasket corresponds to taking the planar map, removing all the loops and its interiors. So I just get a bipartite planar map, Well, this bipartite planar map is distributed again as a Boltzmann planar map, but with a very particular set of weights, which denote Q hat, that are given by explicit formula in terms of the original weights. So the ON loop model is, it has several phases, and in these phases it's conjectured that they have a scaling limit in terms of LQG and CLE for particular values of gamma and kappa related to n. One can again study the peeling exploration of such maps, where now we can not only encounter phases, but we can also encounter loops. Let's see, where shall I go next? So, yeah, let me briefly describe this. So here is a planar map with loops. So these are the green phases. They correspond to the loops for which the phases for which the loops run. And I just explore them all at once, these loops, when I encounter them. But when I have a target in my map that I'm trying to explore, then now and then I have to jump inside of a loop. So I can track kind of the perimeter of the unexplored region containing the marked vertex. It will give me some process, but it's slightly different from the process for the Boltzmann planar maps. But again, it can be obtained from the same random walk S, now associated to the law of Q hat, by some kind of H transform. But now the boundary conditions are slightly different. So let me not go into these details given the limited time. But an important thing to mention is that, okay, the number of times that I go through a loop can actually be extracted from this perimeter process and another process that is a nesting process. And an important fact is that the number of loops and the lengths of the loops that I encounter when targeting this marked vertex really does not depend on the weights of the model. They only depend on the value of n that I've chosen. So here is the result. Given that they really do not depend on the weights that I've put on my planar map, I could as well have done with only loops that go around the marked vertex and suppressed all other loops. And I know how to generate planar maps that have only loops that go around the marked vertex, namely from random walks, by this bijection. So as a result of this, what one gets is that in the special case of n equals 2, so why n equals 2? So the n equals 2 really correspond to the fact that for each loop on this side, I had a plus or minus sign of the loop. So I have a factor of 2 for each loop. Then, if I choose the weight non-generic critical, meaning it's in one of these universality classes that is not the Brownian map, then the number of nested loops in a Boltzmann loop decorated map of perimeter 2L, I denote that by NL. And it's closely related to the winding angle of this random walk when started at 2L before it hits the origin. In fact, the probability generating function on number of loops is exactly equal to the characteristic function of this winding angle, and it's given by an explicit formula. And one can get the similar nesting for the ON loop model with values of n not equal to 2, but just taking this distribution and tilting it by n over 2 to the power number of loops. And this is a result which is closely related to earlier results obtained in particular by Bertrand and collaborators and Nicolas and Lin Xiao. But the nice thing here is that it relates its nesting to winding of random walks, something that had been hardly studied at an exact level before. And this inspired a lot of kind of new exact statistics of the winding of random walks on the lattice. Here's an example. Let me finally conclude. So it would be nice if I have such a two-dimensional random walk that it does not just encode the gasket of an ON loop model, but the full ON loop model map. Because then it would put this encoding in the same kind of ballpark as the mating of tree type encodings of site percolation and uniform triangulations that Nina talked about, but also like the Mullen bijection and spanning tree decorated maps, which allow one to deduce very strong properties about these maps from equivalent properties on LQG plus SLE. Okay, so is there any chance of actually encoding the full map using such an excursion? Well, one should remember that once we do the bijection, we get some faces which are still kind of decorated with excursions. And these excursions can still be large. So what we would like to do is to further decompose these excursions to fill in kind of what sits inside of these large faces in the map. Now the obvious thing to do is, so I have an excursion that starts at 0, ends at positive k minus 2, is just to mirror my excursion. Because I know if I have an excursion that goes from 0 to some negative value, it will encode a planar map again. And I'd like to put this inside of one of these loops. Unfortunately, it's not quite that clean because of the annoying 2's sitting here. So the planar map that such an excursion encodes does not nicely fit into a rigid loop in such a large space. Instead, I have to kind of contract the inner boundary of the loop by 4 to make it fit. Apart from that, in principle, I have kind of a mapping that takes an excursion and it encodes a type of O2 loop model decorated map in which all the loops are kind of asymmetric, inside, outside, and which carry a sign on all of the loops, which kind of explains why I have a O2 model. Now, it would be quite nice to find a version of this bijection which does not require the asymmetry of these loops, and that does not leave any extra decoration on the vertices in the map that I still have. So that's homework, and here's another homework. Try to extend this encoding to n smaller than 2. Okay, thank you. I think I've run out of time.
Thanks a lot. Since we are running a bit late, I propose we contemplate on Timothy's wonderful lecture and start right away the second lecture of this morning. And if you have questions, please ask Timothy during the coffee break. Sorry? No, we are 10 minutes late. So I propose we postpone the question to the coffee break. Okay? Thanks again.